Here's an interesting problem that I've encountered recently. Assume you play an infinite series of games, with the probability that you lose the nth game being 1 over 2 to the power of n plus 1, and the probability that you win being 2 to the power of n over 2 to the power of n plus 1. The condition is that when you lose the nth game, you lose 2 to the power of n dollars, but if you win $1 only. That means you will win small amount of money quite often, while you will lose serious amount of money less frequently. The question is, what is your expected return? One would usually assume it's 0, since by expectation calculation we have that multiplying the probability and the return from the outcome returns this. However, an interesting result from probability theory, namely the Borel-Cantelli Lemma, gives a different result. Before going into the details of the solution of the Borel-Cantelli Lemma, one actually needs to pin down two mathematical concepts, one of which is events happening infinitely often and another is events happening eventually. Imagine you flip a fair coin infinitely many times. Let an be the event that the nth flip is heads. Since the coin is fair, you expect that the heads would come up infinitely often, no matter how many times you flipped it already, even though you can't predict exactly when the heads will turn up. In other words, no matter how many tails you get in a row, there will always be more heads if you keep flipping. Hence, this event is called infinitely often. Now consider a different scenario. Suppose you are saving money every month to buy a new car. Then, define the event an to be the event that you have enough money by the nth month. Then, even though it takes some time, if you continuously save money, there will be eventually a month, call it big N, after which you will always have enough money to buy the car. This means that the event having enough money will always hold, or rather hold eventually. Since once you get the money, you always have it, given of course that you don't spend it. If you wish to get a more mathematical perspective of these concepts and the proof of the first part of the Borel-Cantelli Lemma, you can actually find it at the end of the video because it's quite technical, so it requires more thought. We now have the toolbox to state the Borel-Cantelli Lemma. Given the series of events an, if the sum of the probabilities of an is less than infinity, meaning it converges, then the probability of an happening infinitely often is 0. On the other hand, if the sum of probabilities an equals to infinity and the events are independent, then the probability of an happening infinitely often is 1. This tells us that if the sum of the sequence of probabilities is finite, then the sequence can happen infinitely often. We define the event an to be the loss of nth game. Recall that the probability of losing was 1 over 2 to the power of n plus 1. Then the sum of the probabilities of an is equal to the sum of these probabilities. Of course, because 2 to the power of n plus 1 is bigger than 2 to the power of n, we know that the sum is less than the sum of 1 over 2 to the power of n, which we know already converges. Then, by Borel-Cantelli Lemma part 1, we get that the probability of an happening infinitely often, that is, the probability of losing infinitely often, is 0. So one will only lose finite number of times, and the amount of money won by the player goes to infinity, which is not 0 as expected before. Let's tweak this problem a little bit. Let an still be the probability of losing the nth game, but make the probability of losing 1 over n instead of 1 over 2 to the power of n minus 1. Then the infinite sum, 1 over n, wouldn't converge, and since all of the events are independent, we will have that the losses would always occur. Another famous result of the Borel-Cantelli Lemma is the infinite monkey theorem. Imagine you sit a monkey in front of the keyboard, and let it press keys independently and uniformly forever. Then at some point, any combination of keys will be struck, and that includes the entirety of Hamlet by William Shakespeare. Let k be the number of characters in Hamlet, and t be the number of keys on the keyboard. Then there are t to the power of k possible key combinations, and the probability of an is 1 over the number of possible combinations. Then the sum of probabilities diverges, as adding up the same number infinitely is infinite. Since the events are independent, we have that by Borel-Cantelli 2, probability of the event happening infinitely often is 1, so at some point the monkey will hit keys to write out the entire Hamlet. Now to the mathy part. To express the event happening infinitely often, mathematically, we consider the unions of intersections of an. For simplicity, consider infinite number of independent events a1 to a5. Then denote Bn to be the union of all events ai starting from the nth event. Then we can represent different events b1, b2, and b3 as follows. where the colored circles represent unions. Then for infinite AI and BI, we define AN happening infinitely often as the intersection of the BNs. This definition allows for the proof of Borel-Cantelli Lemma. Recall that the Borel-Cantelli Lemma and the definition of the events happening infinitely often are given by this. Then since AN happening infinitely often is the intersection of events BN, the intersection has to be smaller than the set of BN itself, which is the union of AK. Then naturally, the probability of AN happening infinitely often is less than the probability of the union of AK, which is less or equal to than the sum of probabilities of individual AKs. Since the sum of the probabilities of ANs over all n is finite, by the condition of the lemma, we know that the expression goes to 0. This was a great visualization of how probability theory and measure theory can be applied in real-life situations. Thanks for watching.